Hello. Nice to meet you. This is Mr. So from Metas IT. I'm in charge of a technical manager for building engineering. In today's webinar, I will share main technology of high-rise building design. First, we need to define what a high-rise building is. In the early days, it was simply classified as a high-rise by the slenderness of the building or the number of floors. Even though it is recently difficult to simply define through the numbers due to the advanced technology. Mark Fintel defined a high-rise structure as a building that requires a special structural system to resist lateral loads, from an engineer's point of view. Therefore, in this webinar, I will deal more with efficient lateral force resisting systems. The main technologies required to design a high-rise are as follows. The most important technology in the structural design is the selection of the efficient structural system and control of the lateral displacement. In addition, wind vibration control and prediction of column shortening are also required. And recently applied technologies include a design to prevent a progressive collapse and structural health monitoring under the service status. And representative field engineering includes joint control and hydration heat control. From now on, I will explain these in more detail. The first technical item is about the optimal structural system. One of the most important factors in optimal structural design is economical efficiency. In other words, a competent engineer must be able to design more economically under the same condition. Below is an analysis of frame weight per unit area according to the number of high-rise building floors with RC frames. Here, the frame weight means a construction cost. Curve C with black color is the weight for horizontal members such as slabs and beams. There is no significant increase because this has no effect on the number of floors. Curve B with blue color is the weight including the vertical material. In the case of the column size increases as the story number increases, so the weight gradually increases. Curve A with red color is the weight including the lateral force resistance system. As the story number increases, the increments in weight are caused. The weight of 100-story building increases by about 3 times per area, compared to a 10-story building. If the weight according to the design result exceeds curve A, it means that the uneconomical weight is included in the design. Next is the construction cost ratio by construction type in RC high-rise. The graph on the right shows the construction cost ratio of the conventional RC frame, in which the formwork is half of the total construction cost. In other words, the cost of the formwork occupies an absolute proportion. Therefore, it is important to introduce a structural system that can reduce the cost of the formwork. In order to reduce the formwork cost, it is necessary to minimize the amount of construction period and the formwork area. Therefore, it is important to determine the slab structural system with the largest formwork area. In RC system, the construction period per floor of beam and girder systems generally takes 7 days or more. If the flab slab system is applied, the formwork area will be reduced by more than 30% and the construction period will be reduced by about 50% like 3 or 4 days. This means that the total construction cost is reduced by about 10 to 15%. In addition, the height per floor is also reduced. So the story number can be increased by 10% compared to the same building height. Sales area increment brings out the result that can contribute to securing the economic feasibility of the project. Moreover, the steel system can reduce the process and story height by applying a new construction method. The slim floor system is a representative example of the new methods. The following is a graph comparing the quantity per unit area for each structural material. For the 4 example buildings including Burj Khalifa, the concrete volume of about meter to the third power per unit area was calculated. In the case of rebar, the quantity of about 100 kilograms per unit area was calculated. Some projects like DMC and Trump Tower have somewhat decreased in quantity due to TMD installation. If you design a new project with the RC system and get more volumes compared to these cases, you can find that it is not an economical design. This means that the structural system should be double-checked. So how do we determine the optimal lateral resistance system? First, let's look at the basic arrangement of columns. As you know, it can be considered as an ideal arrangement if the moment of inertia becomes larger when the same number of columns are arranged outside rather than at equal distance. This can be confirmed by evaluating the rigidity index of bending and shear. In the case of bending rigidity, when bending rigidity index concentrated at the corner is assumed to be 100, the equal distance is evaluated as 33 and the edge type of the number 7 is evaluated as 63. For the shear rigidity, the diagonal system is more efficient and the denser the columns are arranged, the higher the shear rigidity becomes. In conclusion, it is possible to find out the difference of resistance performance through this evaluation. Then, let's check which structural system is applied, depending on the story number in general. In the case of steel system, an outrigger and belt truss system can be applied on the 50 to 70 story, and a tube system can be applied for the 70 to 100 story. If there are more than 100 story, a megastructure system is used too. In the case of the RC system, the core and spine wall system can be used for the 50 to 70 story, and the core and tube system can be applied for the 70 to 100 story. It can be used as a reference for the selection of initial system. Let's find out the characteristics of each lateral resistance system. There are outrigger and belt truss systems. These systems increase the lateral resistance performance by transferring the force acting on the core to the external column by way of the coupling effect. Once the systems are installed, the performance is increased by about 30% compared to before installation. If so, where is the most efficient location to install the outrigger and belt truss? As an empirical result, when installed to only one story, the most efficient story is the location corresponding to 45.5% of the building height. When installed to 2 stories, it is the most efficient to respectively install at 33% and 66% of the building height. Despite its efficiency, it is often installed on the top story according to the architectural plan. In this page, I will introduce how to calculate the ratio that contributes to displacement or stiffness for each structural system element. Here is a structure with a core and an outrigger system. For the calculation, the analysis is performed after the structural system elements are added one by one. As the first step, core wall and column are installed. At this time, only the core wall can resist the lateral force because the columns were set as a pin connection. After the outriggers and belt trusses are installed in step 2, the lateral force is resisted by the core wall and the outrigger and belt truss. In step 3, the pin connection of the column is converted to a fixed condition so that the moment frame also resists the lateral force. In the final step, an exterior walls are added to resist lateral forces. The analysis results can be summarized as follows. For each lateral system elements, the representative displacement value can be calculated using the following equation, and the representative stiffness value can be obtained with this value. And the difference in the representative stiffness value for each step becomes the relative stiffness. And if converting this to a ratio, we can get the stiffness participation ratio. It can be judged that the larger this value, the more effective the resistance performance against lateral force in the structure. From the calculation of stiffness participation ratio, the outrigger and belt truss were about 49%. So we can determine that it is the most effective structural element in example structure. Based on these values, you can make economical design by further strengthening the system elements with great effect, or eliminating or reducing the ineffective system. The next system is the spine wall system applied to Burj Khalifa. It is a structural system that resists lateral forces by the walls composited along the internal passage or boundary in plan. In this time, it is necessary to consider the torsion, and it can be solved by constructing a box or triangular-shaped core wall. And the fin wall is a structural system that resists lateral force by installing walls on both sides or one side of the core. In order to improve structural efficiency, it is common to install it up to middle story of the structure. Let's compare the performance of the fin wall system and the outrigger system. Here is an example building with about 60 stories to compare the performances. When comparing the control performance for wind deformation after applying the systems on the example, the fin wall system has analyzed to be about 26% more efficient. However, the fin wall system in which distribute plan spaces is likely to be disadvantages in the use of space for architectural planning. There is an example of analyzing the spine wall and fin wall. Case 1 is to install only a spine wall, and Case 2 is to add a fin wall at spine wall. When comparing performance of Case 1 and Case 2 with the same cross area, Case 2 has twice the stiffness. Therefore, it is effective to apply a fin wall to the end of the spine wall for economical design. The right side is a comparison of the performance when the spine wall is installed continuously in the core, and when it is not. It can be seen that the efficiency increased by 27% when the stiffness and quantity were considered together. When designing a high-rise, we need to check the effect through studies on various cases and determine the optimal system. Below is also a sample of case studies to find the efficient system adding walls or other structural elements. Efficiency is calculated by the ratio of stiffness to volume. First is the study results for Case 1. The following is for Case 2. The coupling beam, spine wall, fin wall, and belt wall were added in that order. Through these case studies, the efficiency of adding a fin wall and an outrigger system can be confirmed. This is a real project example on which applies the previous results. The structural system was developed based on the design result when the architectural plan was reflected as it is. In the first development, unnecessary walls has removed through the stiffness participation ratio. So, the quantity is reduced by about 10% when the performance is the same. In the second development plan, I considered the continuity of the spine wall at the core and the fin wall. That leads the quantity to be additionally reduced further by about 10%. As a result, I improved in economic efficiency by 20% through the process of finding the optimal structural system. The next is a diagram grid system. The digrid structure effectively transmits both the gravitational and lateral loads by configuring the inclined members on the outside of the structure as a grid truss in the form of a diamond. At this time, the angle of the grid makes a difference to the performance of the structure. The axial force of the digrid element by the vertical and lateral forces can be calculated as follows. This page is for the lateral displacement control performance according to the angle of the digrid. As shown in the right graph, high efficiency is obtained for angles between 53 and 76 degrees. Finally, the mega column and brace system. In order to resist both large lateral and vertical loads, the form of large columns and trusses of enormous size is used, and various methods are mixed according to the characteristics of the lateral load. Through the following images, you will be able to understand the structural concept easily. The angle of the mega brace is also very important to the structural efficiency. The following is a review of the performance and quantity according to the angle and shape of the mega brace. In this example, the angle of the brace between 35 degrees and 70 degrees was evaluated most effectively, and the brace module of the building was decided according to this shape. Engineers must make a decision considering both lateral stiffness and quantity according to the shape. For the control of lateral stiffness, the coupling effect between the core walls is very important. There is a very large difference in the moment of inertia when the coupling effect between the walls is considered and when it is not, as shown on the left. So, coupling beams must be designed so that the high coupling effect can be revealed. Since the length of coupling beams are short and the height is large in general, a shear and compression behavior occurs as follows, not bending behavior. Therefore, the seismic resistance details should be equally applied to the design, as shown on the right. The following is for the column shortening. Since I've explained it in detail in the previous webinar, so I'll explain it briefly. As you know, when an axial force acts on a concrete element for a long time, a concrete element will have elastic shortening by loads and inelastic shortening by non-homogeneous properties of material. In the case of the elastic shortening, it is caused by gravity loads. And the inelastic shortening is due to drying shrinkage and creep. The inelastic shortening occurs larger in our high-rise buildings, and there are different shortenings according to the vertical member type, like columns and walls. In particular, the different shortening between vertical members causes a lot of problems in a high-rise building. If we look over the case of a high-rise with 100-story, in the total shortening of vertical members, elastic shortening accounts for 40–50% and inelastic shortening accounts for 50–60% generally. Concrete columns usually have a shortening of 2 to 3 millimeters per story. So the shortening at the roof is about 200 to 300 millimeters. The shortening of wall is about 1 millimeter per story, and the shortening of the roof is about 100 millimeters. Therefore, the difference shortening between column and wall is about 100 to 200 millimeters at roof. It means that when the span between column and wall is 8 meters, it has a very large inclination of L/40 to L/80. Then, what are the problems caused by different shortening? First, it causes usability problems such as damage to finishing materials due to deformation as follows. And the additional member force is added to the horizontal member due to deformation caused by different shortening, which causes safety and serviceability issues like cracks, as described earlier. The first reason is differential shortening of the column and wall. In the case of the wall, the lateral load is an important factor in determining the cross-section. Therefore, the ratio of compressive strength to axial force is generally about 15 to 20%, so it is very small. However, in the case of columns, gravity load is the most important factor, and the ratio of axial force and compressive strength is about 40 to 50%. Therefore, a greater vertical strain occurs in the column than in the wall. For this reason, an additional member force is generated in the horizontal member by differential shortening. So what is the solution for a differential shortening? First of all, the serviceability problem is solved through correction when pouring columns and walls. The pouring level of the vertical member is corrected so that the final shortening reaches the planned level and has a similar level to each vertical members. For this, it is important to calculate the correction value exactly. If the predicted shortening does not occur after the correction, problems may arise due to that. Next is the solution for additional member force. Since this does not remove by the correction, the additional reinforcing bars must be calculated through CS analysis at the design stage and reflected in the drawing. Next is for the entire process of the column shortening project. In the initial structural design stage, the first construction stage analysis is performed by applying the basic inelastic material model and the assumed construction process. This is called preliminary analysis. In the design step, reinforcement for additional member forces is reflected through this preliminary analysis. Next, once the construction site is opened, material experiments are conducted. Through this experiment, the curve of the compressive strength, modulus of elasticity, creep and drying shrinkage are obtained. Secondary analysis are performed by reflecting these experimental values and the actual construction process plan. This is called basic analysis. Finally, the third construction stage analysis is performed in consideration of the changed construction process and construction environment. This is called main analysis. Through the accurate prediction considering the measured shortening on the site, construction corrections for the shortening of the upper story that has not yet been poured should be performed. Here is considerations for the structural design step. First, you need to control the arrangement and size of columns when designing the plan. Columns adjacent to walls are repositioned to have as long distance as possible. And the size of the columns is determined so that similar compressive stresses are applied between adjacent columns. The following is the progress of the column shortening project using Gen. First, create a group for members, loads and boundary elements in order to set the construction stage. And each construction stage should be defined by assigning the group information depending on the construction schedule. Next, we need to define the time-dependent material properties, such as creep, shrinkage, and compressive strength. And then links each defined material properties to each members. The analysis can be performed using the defined construction stage and inelastic material information. We can obtain the member force for each gravity loads, creep and drying shrinkage through this analysis, and can create a load combination including a wind and seismic load. Now, it is possible to do a design that reflects the column shortening using these load combinations. And the shortening of each vertical member can be obtained from the analysis result as well. And we can calculate the amount of correction by using these shortening values. Gen is supporting the load combination function in order to design considering a results of construction stage. When generating a load combination as follows, we can use the load case in creep and shrinkage loads, and you can combine an earthquake load and wind load too. Of course, it provides basic auto-generation of load combination. Final procedure is the calculation of the shortening value of the vertical member. Gen provides the shortening value of the creep, shrinkage, and elastic shrinkage of the specific nodes as follows. The function of extracting a graph as Excel data is provided as well. Through these shortening values, the vertical correction value can be calculated. Next, for the wind design. Because a very large and atypical wind load acts on a high rise, the wind design is the most important one in the high rise design. 3. Representative wind effects greatly affects to the high rise building. First is the occurrence of the turbulence and Venturi effect. Due to this phenomenon, disordered and abnormal wind loads occur around the structure. So, the wind load for the high rise has a big difference from the wind load as per the normal design code. Next is the gust effect. Since the flexible structures are more affected by the gust effect, this effect should be specifically considered for the high-rise buildings. Finally, the vortices effect. It applies alternating and repetitive wind loads on both sides of the building, causing large vibrations. Therefore, solving the usability problem due to large deformation and vibration in the orthogonal direction of the wind is an important point in high-rise building. The wind tunnel test is mainly used as a method to solve the problems by the wind effects described above. Wind tunnel tests include wind force test, wind pressure test, and wind environment test. Firstly, from the wind force test, we can verify a building's safety and usability against wind vibration and get the acquisition of wind load for design. The data which we can get is air force coefficient, wind load spectrum, vibration displacement, shear force, overturning moment, and torsional moment. And from the wind pressure test, we can investigate the wind pressure acting on the building and its characteristics, and get the acquisition of wind pressure for exterior material design, like a cladding and canopy. The result data is the wind pressure coefficient. The wind environment test is performed to evaluate comfort and safety of pedestrians near the building. The wind flow pattern around the tall building can create unexpected currents with different speeds. The next solution is to reduce the wind effect through the geometry of the building. There is a comparison of wind force for various shapes with the same plan area. When the square plan is set as the criterion shape, a larger wind load is applied to the rectangular and triangular compared to other shapes. It indicates that the round shape, corner chamfered shape, and cut shape are very effective in reducing wind load. In the elevation shape, there is a great load reduction effect when the four-sided tapered shape and the setback shape are applied. And when the cross opening is installed on the top of the building, it tends to have a great effect on reducing the across wind overturning moment. In previous page, I explained the method for accurate judgment and reduction of wind load. On this page, how to control wind vibration will be explained. First is the aerodynamic design. The aerodynamic design is a way to reduce wind vibration by changing the shape of the building, which can be suggested by structural engineers during the initial construction plan. The following is a method to control through the increase or decrease of mass and stiffness in structural design. When the method is applied, mass is increased, the wind vibration is reduced, but the seismic load may be increased, so be careful. The last is to apply the vibration control device such as TMD. In aerodynamic design, similar to wind force, corner chamfered and cut shape are very effective. And the helical square shape also has a great reduction effect. In the case of a vibration control device, vibration is reduced as shown in the following conceptual image. The structure responses are reduced by moving the mass device in the opposite direction to the building's movement. In the case of the project that I actually designed, it was evaluated that when TMD was installed, the wind vibration was reduced by more than 40% and the seismic vibration reduced by more than 20%. Next is structural health monitoring. It may be unfamiliar, but I would like to introduce it since it is a technology that has been tried a lot recently. Structural health monitoring is an integrated system that monitors buildings in real time using advanced measurement technology to evaluate and guarantees a safety objectively. and maintains and manages to maximize the sustainable time of buildings quantitatively. Why is the market introducing structural health monitoring? First is a relief of structural anxiety about high-rise buildings. The second benefit is to economize a customary safety inspection costs with regular monitoring. Next, it can minimize the risk of accidents through appropriate responses in extreme situations like in earthquakes, typhoons, and other disasters. And it can make a maximization of a lifetime of building. Last is the engineers can get the optimal guidelines for structural design by identifying the characteristics of high-rise structures. The integrated system for structural health monitoring consists of the following. First, the measuring unit. It is a system that measures the response of external stimuli and structures. For monitoring external stimuli, wind direction, anemometer and accelerometer for earthquake measurement are generally installed. In addition, for structural response measurement, GPS and accelerometers are installed on roof and multiple story. GPS is for displacement measurement and accelerometer is for structural acceleration and mode shape. And under an emergency status, we can determine whether the member is damaged through the strain gauge. Next is the information transfer unit. Both wired and wireless can be used. But in the case of wireless, time delay may cause errors in result analysis, so wired is recommended. Next is the analysis unit. Here, an internal analysis tool is used to evaluate the safety and stability of the structure. If the evaluation result exceeds the set risk level, it is transmitted to the user and facility manager through the alarming unit. What should engineers do for structural health monitoring? First, you need to decide where the instruments should be installed. In case of the strain gauge, select a member that is expected to be damaged through an inelastic analysis, such as pushover or time history analysis, and decides the location where the greatest stress is expected in target member through detailed analysis like FEM analysis again. Next, because it is necessary to monitor whether the period and mode shape of the building are in the normal range, the accelerometer should be installed on the story and plan location where the main mode shape can be determined most efficiently as follows. Next, the engineer must create a damage assessment system. The procedure of the damage assessment system is as follows. First, compare the natural period measured when an event occurs with the natural period of the analysis result. At this time, the analysis model should be modified so that it coincides with the normally measured natural period in advance. If there is a significant change in the measured period, the dynamic characteristics are analyzed through the measured results and the damage is predicted by comparing it with the damage scenario DB. If there is a measuring instrument in the predicted damage member, the degree of damage is identified through the measured result. And in the case of a member without a measuring instrument, a quick diagnosis is made. The safety reports are provided through the measurement and diagnosis results. And if necessary, the system must control the resident through an alarm. In this process, the engineer must create a damage scenario DB. The DB creation process is as follows. First, an analysis model with the same behavior as the actual structure is created. In case of the member with high possibility of damage, the member stiffness is reduced through nonlinear analysis, and the dynamic characteristics changed through model analysis are analyzed and added to the scenario DB. DB is completed through repetition of this process. To save time, effectively create damage scenarios. Next, we need to establish an alarm system. An alarm system is needed for an alarm to external stimuli and the response of the structure. For external stimuli, the measured value compares with the design load and provides an alarm at 2 levels of caution and wearing. In response to the structure response, it provides an alarm in 4 levels of safety, caution, warning, and danger. It is for the measured period, roof displacement, and stress. The left is an example of building an evaluation level for deformation. Safety means elastic status. Caution means plastic status of coupling beam. Warning is when plastic hinges occur in major lateral resistance system elements, such as outriggers. And finally, danger is when lateral resistance system failure occurs. The right is the evaluation level for the stress of the steel member. Safety means the member stress in within the buckling strength, considering the strength reduction factor. Caution is when it is within the buckling strength not considered. Warning was set within the yield strength, in which the strength reduction factor was considered. And finally, danger was set when this value was exceeded. Next is the design to prevent progressive collapse. A collapse phenomenon in which local and structural damage caused by an abnormal load, such as an impact load or an explosion load, leads to the collapse of the entire structure. Therefore, the engineers must design in structural design stage so that progressive collapse does not occur. As I think, you can understand the progressive collapse easily through the examples of the World Trade Center and Murray Building below. After such an accident, interest in the design to prevent the progressive collapse has increased. So, how should we do for the design to prevent chain collapse? When damage to a specific column occurs, a large member force occurs in the beam as follows. However, due to the very long length of the beam, compression arch action occurs, and the beam is converted into catenary action through the transition phase. At this time, the concept of chain collapse prevention design is to design so that the catenary action can be maintained. In the steel structure, the most weak part to catenary action is the joint of column and beam, and damage occurs due to the generation of intensive tensile force on the column web of the joint. The right side is an example of a detail to prevent damage to the joint. In the case of RC structure, catenary action is maintained through the connection of moment rebars and stirrup rebars. The spacing of the rebars is an important factor to maintain catenary action, and the following details are applied to enhance performance. For the continuity of the tensile load, an X-bar is added to the end, and the bottom rebar is continuously arranged at the column joint. Then how do we judge whether the cross-section of steel or the rebar of RC beam can maintain safety against catenary action? FEMA 2.7.4 provides a design guide for evaluating this. Although it provides a variety of methods, the easiest to apply is the alternative path method. It is to assume that one structural element is destroyed by an abnormal load, and to check the limit state of the elements in order to know if the remaining structural elements can transmit the load well. There are linear and nonlinear methods in the alternative path method. The linear analysis method is a way of comparing the ratio and allowable value of the required performance and capability of the member as shown on the left. If the DCR does not exceed the allowable value, it can be evaluated that the catenary action is maintained. The nonlinear analysis method is a method of comparing the ductility and rotation angle of the hinge occurring in the member with the allowable values. The table on the right shows the allowable ductility and rotations. I would like to explain more about the static linear analysis method that can be reviewed at the design stage. First, remove the target column from the model, and the analysis is performed after applying twice the service load in the relevant area. Demand capacity ration is calculated from the member force by analysis and the strength value by the input rebar. In this case, the strength reduction factor is not generally applied when calculating the member strength. The allowed values for the calculated DCR are as in the table on the right. In the case of general RC structure, it is 2 for the regular type and 1.5 for the irregular type. If the DCR is evaluated to be greater than the allowable value, the end of the member is converted to a pin, analysis is performed again, and the process of recalculating the DCR is repeated until the results converge. If all members are converted to pins through repeated evaluation, it means the progressive collapse will occur. In this case, it is necessary to increase the member's strength through redesign and perform the evaluation process repeatedly until converging to a safe state. The right side is an evaluation case for a steel frame. In the third evaluation, it was evaluated that pins occurred in all parts, and the progressive collapse occurred. Lastly, it is a representative engineering task that occurs during the construction of high-rise buildings. First, the joint installation between the outrigger and the vertical member. In the case of belt trusses and outriggers with very high rigidity against vertical displacement, even a very small difference shortening can cause the problems by a very large stress as follows. Therefore, it is necessary to prepare countermeasures for differential shortening in advance. There are three countermeasures as follows. The first is to perform a unified construction without joints. It must be reinforced so that the strength can be satisfied with the stress generated at this time. Next, install the adjustment joint or delay joint. Two joints prevent a stress due to different shortening occurring during construction by separating the column and the outrigger. And it is the same to minimize additional stress by connecting the joint when construction is finished. The difference of two-way is the adjustment joint can resist, and the delay joints don't during construction. Therefore, in the case of delay joints, safety and stability reviews for lateral forces must be separately performed during construction. This picture on the screen is the detail of the delay joint. Let's talk a little more about the adjustment joint. First, separate the column and outrigger through the following details. Then, insert the shim plate so that there is a gap of about 3 mm between the separated spaces. At this time, when a lateral force is generated, the force can be transmitted to the column through the shim plate, so it can serve as a lateral resistance system. Next, the upper gap is closed when the column shrinkage occurs. Then, the upper shim plate is partially removed through jacking, and the lower shim plate is added to maintain the gap at 3 mm. This is repeatedly controlled during the construction period and connect when the construction is completed. And safety of joint should be reviewed for added subsequent stresses. Establishing joint plans between high-rise and low-rise is an important part as well. First, large additional stress generated in the horizontal member joining the high-rise and low-rise is occurred by the different column shortening due to the different loading, different story number, and the different nonlinear deformation of the concrete. In addition, additional horizontal tensile or compressive force is generated by the drying shrinkage in the horizontal direction. There are three cases for the solution. Case 1 is to calculate the additional stress and reflect it in the design to increase the member's capacity. Case 2 is to minimize the additional member force by installing a delay joint, separating it during the construction period, and connecting it at the end. Case 3 is to permanently separate them so that they do not interfere with each other. The following is an example of Case 1. On the both sides, the high-rise building is located, and a wide podium is located in the middle of the plan. It seemed that cracks is likely to occur in the slab of the podium. To prevent the cracks, the construction process was planned with a time difference by dividing the area into small units. After a long time, a delay joint was installed in the part where the high-rise and podium contacted. This is the comparison for the two analysis. Analysis 1 is the result without considering the construction process and joints, and Analysis 2 is the result from considering the construction process and delay joints. When the stresses at the target point were compared to, the result of Analysis 2 is reduced to about 35% of the Analysis 1. As a result, it is evaluated that cracks won't occur. The next is an example of the analysis sequence for the example structure. Each construction area is analyzed in order. After the entire horizontal member is installed, joints can be connected and analyzed. Next is the splint and pour of slab. It should be poured after dividing into zones, since it cannot be done at once due to the huge size of the plan. So engineers need to have a determination of the location of the construction joint and check the construction joint detail. And the high-rise is almost constructed by the core first method as the picture. Core first method is applied for quick construction and improvement of constructability. So, the detail at joint of core, wall, and slab is needed as the right detail. Next is the hydration of mass concrete like foundation. In mass concrete, the heat is generated by the chemical reaction of concrete. But the external face is exposed to the air, and the temperature decreases rapidly, and the internal concrete temperature is continuously risen. The internal concrete is expanded, and the external concrete is shrank as follows. This causes large cracks on the face. Thank you.